In the last class, we discussed the Stern-Gerlach experiment. In this experiment, we sent a beam of silver atoms through an inhomogeneous magnetic field. We found that when passing through the inhomogeneous magnetic field, the beam split into two. The beam split into two different beams. And based on classical calculations, we found that these two beams corresponded to two possible values for the spin. Okay, one would be plus h cross divided by 2 and the other one minus h cross divided by 2. So based on this, we said that spin is actually quantized. We call this as the spin quantization. This means that if you project the spin vector along the direction of a given magnetic field, it can take only two different values, never in between. Now let's go a little bit further with this Stern-Gerlach arrangement. Sequential Stern-Gerlach experiments. So by this we mean that the atomic beam goes through two or more Stern-Gerlach apparatuses in sequence. Okay, instead of passing the atomic beam through one apparatus, we'll pass them through a sequence of apparatuses. The first arrangement is like this. We have got this oven here where we have heated silver atoms coming out of the oven, and then the first apparatus is denoted as SGZ hat. By SGZ hat, what we mean is that in this case the magnetic field is along the inhomogeneous magnetic field is along the z direction. So the z hat here means gives the direction of the inhomogeneous magnetic field. So this is the first arrangement that we had considered. This is what we denote as the SGZ hat arrangement. So we subject the beam coming out of the oven to an inhomogeneous magnetic field in the z direction as usual. And as we expect, there are two components coming out. One we call as the SZ plus component and the other one as the SZ minus component. Okay. Now what we do is that we block this SZ minus component. The second component we are going to block. Okay. Now we have only the SZ plus component that we again send to another SGZ hat apparatus. Right. So this apparatus is identical to this. Both have magnetic fields along the Z direction. Okay. So this SZ plus component is then fed into another SGZ hat apparatus. All right. And what do we expect? Obviously, out of the SGZ hat apparatus, we get just one beam because the other beam was blocked. Okay. We only get the SZ plus component. This is what would happen in an experiment like this. All right. So there is no SZ minus component because we already blocked it here. This is fine. Okay. So remember that we are sending a large number of atoms here. And you can think of this as blocking all the atoms with an SZ minus component. All right, we are blocking all those atoms and we are sending into the second apparatus only those atoms with an SZ plus component. And obviously, if you measure the Z component of spin, you will get again SZ plus, okay, plus H cross divided by 2. This time there is only one beam component that comes out of the second apparatus, just the SZ plus component. This is perhaps not very surprising. After all, all the atom spins are up. They are expected to remain so. Right? So there is nothing that changes the spin of the atom in between. In between these two apparatuses, there is nothing that changes the spin of the atom. There is nothing that flips or changes the direction of the spin. Okay, so this is exactly as we expect. Now, a little more interesting is the arrangement shown here in this picture. So what we do here is that the first apparatus is again SGZ hat in the sense that the magnetic field is again along the Z direction. All right, and as usual, we'll get an SZ plus beam and an SZ minus beam. That's fine, right? Now we block the SZ minus beam again, as in the previous experiment. All right. Now instead of feeding this SZ plus beam into an SGZ hat apparatus, we are feeding it into an SGX hat apparatus. Okay. This X hat here means that the magnetic field is now in the X direction. All right. And then the result that we get is that we have got an SX plus beam and an SX minus beam. All right. So what happens here is that we are feeding an SZ plus beam into an SGX hat apparatus, and then it splits it into two beams. Okay, one with again H cross divided by 2 along the x-axis and minus H cross divided by 2 along the x-axis. All right, so these two projections are along the x direction. Okay, so the apparatus is the same as before, but the second one has an inhomogeneous magnetic field in the x direction. The SZ plus beam that enters the second apparatus is now split into two components, an SX plus component and an SX minus component with equal intensities. Okay, the probabilities or the intensities are the same. The number of atoms in the SX plus beam are the same as the number of atoms in the SX minus beam. Now, how can we explain this? How can we explain this? All right. So, based on our classical intuition, our first guess would be that some atoms have both SZ plus, some atoms are characterized by both SZ plus and SX plus. All right. The other atoms that are characterized by SZ plus and SX minus. Okay, this is what we would guess. All right, that's what we have here. Does this experimental outcome mean that 50% of the atoms in the SZ plus beam, right, the SZ plus beam, we are asking whether 50% of these atoms in this beam are made up of atoms characterized by SZ plus and SX plus. That these would be the atoms that we get in this beam. All right. So this is the question we are asking. Are these beams, all right, are these atoms characterized by both SZ plus and SX plus? So let me write it here. Are these atoms characterized by both SZ plus and SX plus? And these atoms characterized by SZ plus and SX minus? Okay, this is the question we ask, or this is our first guess. Right? But we'll see that such a picture does not explain the problem. All right? It runs into difficulty. We can see this by doing one more experiment. All right? By using one more Stern-Gerlach arrangement. Okay. So we now consider a third step, the arrangement shown in figure C. All right? This is the figure. Right? This is the arrangement that we are going to use next. Okay. What we do here is that, so the first step, we have got an SGZ hat apparatus and it has an SZ plus beam and an SZ minus beam. We again block the SZ plus beam. Fine. Then, just as in the previous experiment, we send it to an SGX hat apparatus, right, where the magnetic field is in the x direction. All right. Now again, as in the previous case, we'll get an SX plus beam and an SX minus beam. All right. Now what was our guess? Our guess was that this beam is characterized by atoms with both SZ plus, because we have filtered SZ minus away, both SZ plus and SX plus, and this beam corresponds to both SZ plus and SX minus. This is what we guessed. Now let's block this beam again. Right? Let's block these atoms again. Now again we feed this SX plus beam into an SGZ hat apparatus. All right, where the magnetic field is in the Z direction. And what do we get? Again, all right, if you do this, you'll again get an SZ plus beam and an SZ minus beam. All right. Now, if this was true, if our first guess was true, if these atoms were characterized by SZ plus and SX plus, if we feed it into an SGZ hat apparatus, we should have got only the SZ plus beam. All right, but we are getting SZ plus beam and an SZ minus beam, even though we had blocked all the atoms with an SZ minus component earlier. But after passing through an SGX hat apparatus, we are getting back the SZ minus component. All right. So two components emerge from the third apparatus, not one. The emerging beams are seen to have both SZ plus component and an SZ minus component. This is a bit surprising. This is actually totally surprising. This is a complete surprise because after the atoms emerged from the first apparatus, we made sure that the SZ minus component was completely blocked. How is it possible that the SZ minus component, which we thought we eliminated, again it reappears. All right, this SZ minus component actually reappears. The model in which the atoms entering the third apparatus are visualized to have both SZ plus and SX plus is clearly unsatisfactory. Okay, why? Because if this beam, as we said, is characterized by SZ plus and SX plus, if you send it to an SGZ hat apparatus, we should get only this beam. We should not get this beam, right? But we are getting both beams. This means that the beam coming out of the SGX hat apparatus, right? The beam coming out of the SGX hat apparatus, actually the SX plus beam, does not have a definite, the atoms in this beam do not have a definite SZ component. They do not have a definite SZ component, all right? Half of the atoms pick up an SZ plus component and half of them pick up an SZ minus component, okay? This is problematic, okay? We actually see that if the beam corresponds to a definite value for Sx, then its Sz value is completely uncertain. All right. So here we are seeing something similar to this position momentum uncertainty, which you might have studied before. All right. You might have studied that if the position is completely certain, the momentum becomes completely uncertain. It becomes infinitely uncertain, etc. Okay. Here, this is actually what's happening. All right. If you are certain about the x component of the spin, right? Because we know that the atoms in this beam have a definite value of spin along the x direction, right? It has a definite value for Sx plus, right? So this means that if you know the x component of spin definitely, then the z component of spin becomes completely uncertain. Right? So this is very similar to the uncertainty principle that you might have studied in case of position and momentum. When position is certain, momentum becomes completely uncertain. Here what happens, when the x component of the spin is certain, the z component is becoming completely uncertain. Why do we say that this is completely uncertain? Because there are only two possibilities and it could be any of it. So it is complete uncertainty. Okay. So this example is often used to illustrate that in quantum mechanics, we cannot determine both Sz and Sx simultaneously. All right. So this seems to suggest that you cannot determine Sz and Sx at the same time, just like we cannot determine the position and momentum at the same time. More precisely, we can say that the selection of Sx plus beam by the second apparatus, okay, completely destroys any previous information about Sz. Okay. This is what it means. Okay. So this beam is characterized by Sz plus. Right? Why? Because if you again send this beam again, if you feed it into an SGZ hat apparatus, we see that we get only one beam which is characterized by Sz plus. Okay, we don't have Sz minus beam when you pass it through an SGZ hat apparatus. All right. Now, instead of passing this beam to an SGZ hat apparatus, we passed it to an SGX hat apparatus. All right. And then again we analyzed, okay, before passing this directly to an SGZ hat apparatus, we passed it to an SGX hat apparatus. Now again you are sending it, you are feeding it into an SGZ hat apparatus, and you see that the beam has picked up both SZ plus and SZ minus components. All right. So what happens is that this information, the information that this beam is an SZ plus beam, all right, the information that this beam is an SZ plus beam, it's completely characterized by SZ plus. This is lost when you pass it through an SGX hat apparatus. Okay, this information is gone, it's destroyed. All right. Now, once it passes through an SGX hat apparatus, the atoms in the beam don't remember that they were characterized by SZ plus. Okay, how do we know this? Now, after passing through SGX hat, if you feed it into an SGZ hat, you see that it has both SZ plus and SZ minus components. Okay, this is how we know that the information, this particular information, is destroyed once it passes through the SGX hat apparatus. Okay, so from here we actually see that if the beam has a definite value for SZ plus, okay, if the beam has a definite value for SZ plus, the Sx component, all right, the x component of spin is completely uncertain. It could be either Sx plus or Sx minus, right? Now, if the beam is characterized by an Sx plus beam, all right, if the beam is characterized by a plus h cross by 2 spin along the x direction, if the beam is characterized by Sx plus, then it could have both Sz plus and Sz minus components. All right. So this means that if the z component of spin is definite, the x component of spin is uncertain. Right. It could be either of it could be either Sx plus or Sx minus. Okay. Similarly, if the beam is characterized by Sx plus, okay, then the z component of spin is completely uncertain. So if you have a definite spin along the x direction, if you have a definite spin component along the x direction, then the z component of spin is completely uncertain. In the same way, if you have a definite z value of if you have a definite z component spin, then the x component of spin becomes completely uncertain. Okay. All right. So we can say that the selection of the Sx plus beam by the second apparatus completely destroys any previous information about Sz. Okay. Now we could actually compare the situation with that of a spinning top in classical mechanics. All right. So we already are familiar with the word spin from classical mechanics. In the case of a classical mechanical system, their spin is actually orbital angular momentum. Okay. In the case of classical mechanics, we have no such problem. What we see here is that we cannot determine both Sx and Sz. Okay, we cannot determine both Sz and Sx simultaneously. All right, or the atoms do not have both Sz and Sx components at the same time. Okay, in the case of a spinning top, we can write the angular momentum as L is equal to I omega, where I is the moment of inertia. Now the omega can be found. Okay, the omega can be found, the angular velocity, you can calculate it, and by observing how fast the object is spinning and in which direction, all right, how fast and in which direction, we can actually find omega x, omega y, and omega z simultaneously. Now, if you know omega x, omega y, and omega z, you can also find the moment of inertia depending on the geometric shape of the spinning top, etc. You know how to calculate the moment of inertia. It has a definite moment of inertia. You can also find Lx, Ly, and Lz, or the spin of the top. Okay, you can find all, let's say, Sx, Sy, and Sz simultaneously. Okay, in classical mechanics, there is nothing that stops from finding all the components of angular momentum at the same time. But in quantum mechanics, this is not the case. Okay, so there's no difficulty in specifying both Lz and Lx in the classical situation. You can always do that. We have been doing this. All right. Now, it is to be clearly understood that the limitation we have encountered in determining Sz and Sx is not due to the incompetence of the experimentalist. Okay, this is not the problem with our experiments. Okay, you can make your experiment as good as possible, and still this kind of uncertainty will still be there. All right, so it's not a problem with our experiments. This is something more fundamental. All right, and it is related to a basic fundamental quantum mechanical nature. Okay. So by improving the experimental techniques, we cannot make the Sz minus component out of the third apparatus disappear. All right. So the problem for us is that there's an Sz minus component appearing here, even though we had filtered it out here. All right. Once we determine the x component of spin, all right, once we characterize the beam by Sx plus, then the z component of spin becomes completely uncertain. Right? There's nothing we can do about this. This is fundamental quantum nature. All right? So we cannot make this Sz minus beam disappear by improving our experimental setup. The peculiarities of quantum mechanics are imposed upon us by the experiment itself. All right? So nature imposes upon us these peculiarities. It's not any problem with our experimental setup. The limitation is in fact inherent in microscopic phenomena. All right? The fundamental reason for this is basically superposition of states. Superposition of states. Okay. We had already discussed the superposition of states in relation to a double slit experiment. We said that a single electron can be in both slits. Okay, it could be at different places at the same time. And we said that the state of the electron can be written like this: slit 1 at a particular time. Right, beam that passes through slit 1 and beam passes through slit 2. Right? This is superposition. It can be at two states at the same time. All right. Actually, we'll see later on that this is exactly what's happening here. If you have an Sz plus beam, that if you have an Sz plus beam, it is simultaneously, it actually has simultaneously Sx plus and Sx minus components. All right. But when you make a measurement, we'll never see it in superposition. It reduces either to this or to this possibility. Right. Similarly, if you take an electron characterized by Sx plus, you will see that it's simultaneously in Sz plus state and Sz minus state. Okay, this is the reason for this kind of uncertainty appearing. All right, so if you have a beam characterized by Sz plus, it is simultaneously in Sx plus and Sx minus. states. Okay, this is principle of superposition. Right? But when you make a measurement, you never find it in superposition. It reduces either to this possibility or to this possibility. That's why it becomes uncertain. All right. Similarly, if an electron is characterized by Sx plus spin, all right, it is simultaneously in Sz plus and Sz minus. But if you choose to make a measurement of the spin, it will either reduce to this state or to this state. Okay, this is the reason for the quantum mechanical uncertainty that we have seen here. Right, but of course we have not started looking at the mathematical framework. I'm just giving a hint of what we are going to see. All right. And we'll actually make all these things more concrete. We'll study them. We'll actually develop a mathematical formalism based on these ideas. And I suggest that you revisit the Stern-Gerlach experiment once we have discussed the complete mathematical formulation. All right? And then these things will make more sense. All right. For now, these are just a set of confusing experimental results. All right. So this is the kind of behavior we want to describe using mathematics of quantum mechanics.